It's not the explosions that break ships, it's the water itself. Naval weaponry evolved around one critical factor: inertia. A ship is the ultimate kinetic energy storage device. Thousands of years ago, engineers realized that the vessel itself was the primary projectile, and the ocean was a massive conductor for the impact. It all started with the ram. This was a massive bronze structure mounted precisely at the waterline. The engineering challenge was immense. You had to accelerate a multi-ton craft to a speed of 10 to 12 knots using 100 synchronized rowers. At the moment of collision, all that stored energy was focused into a single point, just a few square inches in size. An impact of that magnitude instantly shredded the wood fibers of the enemy's hull, creating a breach that was physically impossible to patch in the heat of battle. But the ultimate engineering puzzle was the recoil. If the ram was attached too rigidly, the impact energy would kick back into the ship's own frame, destroying it from the inside out. To solve this, ancient shipbuilders developed a system of internal timbers, a skeleton, that distributed the force of the blow throughout the entire hull, dampening the inertia. This transformed the ship into the world's first guided missile, weighing hundreds of tons. Phase 2, Greek fire, pressure chemistry, and the first flamethrower. When ramming tactics became obsolete due to the rise of more maneuverable vessels, Byzantine engineers took a radical leap. They transformed the ship into a floating chemical lab. In the 7th century, a weapon emerged whose recipe remained a state secret for 500 years: Greek fire. This wasn't just a mixture thrown in pots. It was history's first sophisticated mechanical flame-throwing system, the siphon. The technical specs: at the heart of the system sat a sealed copper tank filled with a combustible mixture, likely crude oil, resin, sulfur, and saltpeter. But the real engineering trick was the pressurization. Using hand pumps, air was forced into the reservoir to build up immense pressure. When the valve was flipped, the mixture erupted through a bronze tube, the siphon. The physics of the strike: an open flame, a brazier, sat at the nozzle's exit. As the mixture shot through it, it ignited into a jet of liquid fire that could reach 30 to 50 feet. But the most terrifying part was its adhesive properties. It stuck to wood, to clothing, and to skin. Because of the petroleum base, the mixture was lighter than water. Attempting to douse it only spread the flames across the sea's surface, creating burning traps around enemy ships. Phase 3. The Age of Gunpowder, Broadside Ballistics and Recoil Energy. With the advent of gunpowder, naval weaponry took a colossal leap from chemical mixtures to pure metallurgy. The engineer's task was no longer just to set the enemy on fire, but to punch through their hull with a 30-pound iron cannonball. This reshaped ship architecture entirely, turning vessels into floating batteries. The engineering challenge: cannons on deck. The primary issue for designers was recoil. When a cast-iron cannon fired a ball, the expanding powder gases pushed the barrel backward with immense force. If the cannon were fixed rigidly, the energy of the shot would simply rip out a section of the deck or capsize the ship. The solution was the wheeled gun carriage and a complex system of ropes, breeching ropes. Upon firing, the cannon rolled back, dampening the energy through its own mass and the friction of the wheels against the wood. This was history's first effective impulse-dampening system on a mobile platform. The physics of the broadside. To maximize firepower, engineers began lining up cannons in rows along the sides, giving birth to gun decks. A simultaneous broadside from all guns on one side created incredible pressure. But this introduced a new risk: the law of conservation of momentum. If a ship fired all its heavy calibers at once, the reactive force could cause a severe heel or even flip the vessel, especially if it had a narrow beam. Specialized munitions. Engineers of the past developed an entire arsenal for different physical tasks. Chain shot, 2 balls joined by a chain. Their physics relied on centrifugal force. In flight, the 2 balls would spin, stretching the chain taut and acting like a giant blade that sheared through masts and shredded sails. Canister shot, grape shot. This turned the cannon into a giant shotgun, creating a cloud of projectiles to clear the enemy deck. This was an era where victory depended on how precisely you calculated the elevation angle and how fast your crew could manhandle a multi-ton piece of iron dancing across the deck after every shot. Now we move to Phase 4. Here we dive underwater, where the physics becomes even more aggressive. This is the moment engineers realize that air is too weak a conductor for an explosion and that the true destructive power hides within the density of water. Phase 4. Torpedoes and Hydrostatic Shock. The invisible breach. When ships grew thick layers of iron armor, cannonballs began simply bouncing off their hulls. Engineering logic took a 180-degree turn and went beneath the surface. This led to the birth of the weapon that changed naval strategy forever, the self-propelled mine, known today as the torpedo. The technical breakthrough, Whitehead's first torpedo. In the 1860s, Robert Whitehead solved the most complex engineering puzzle of the era: how to keep a projectile moving steadily at a fixed depth underwater. He invented the secret hydrostatic apparatus, the mechanical brain of the torpedo. It was a system of springs and membranes that reacted to water pressure. If the torpedo sank too deep, the pressure pressed against the membrane, which used a series of linkages to adjust the horizontal rudders and bring the projectile back up. This was history's first autopilot system, powered entirely by the physics of pressure. The physics of destruction. Why is it worse underwater? The torpedo's true secret wasn't the explosion itself, but how water transmits energy. When a torpedo detonates near a ship's hull, it creates a phenomenon known as water hammer, hydrostatic shock. Because water is nearly incompressible, it transfers the entire energy of the detonation directly into the ship's structure. But the most fascinating part happens a fraction of a second later. The explosion creates a massive gas bubble beneath the ship. When this bubble collapses, the water rushes back in at incredible speeds. The ship, suddenly losing its buoyancy support under the keel, literally sags in the air and snaps in half under its own weight. Phase 5. Missiles and Smart Ballistics. With the rise of guided missiles, naval weaponry finally moved away from massive cannons. Engineers faced a new physical obstacle: the curvature of the Earth. If an enemy ship is 60 miles away, you simply cannot see it. This gave birth to the concept of the over-the-horizon strike, where the anti-ship missile became the star of the show. The technical components, seeker heads, and sea-skimming. The main challenge was teaching a missile to find its target in the vastness of the open ocean. Engineers developed active radar homing seekers. The missile emits a radio signal that bounces off the enemy's metal hull, allowing the onboard computer to correct its course. But the most fascinating physics lies in the flight profile. To avoid early detection by enemy radar, the missile performs a sea-skimming maneuver, flying literally 10 to 15 feet above the crests of the waves. This is an incredible engineering feat. The missile must travel at subsonic or supersonic speeds while constantly measuring its distance to the water using a radio altimeter, staying low enough to avoid crashing into a wave, but not so high that it exposes itself to air defenses. The physics of shaped charge and HE, high explosive, impacts. Unlike a cannonball or a torpedo, a missile carries a warhead designed around directed energy. Upon impact, it generates colossal pressure that literally burns or punches through armor into the hull. Yet modern naval weaponry has gone even further with the advent of hypersonic missiles. Here, pure kinetic energy returns, just like in the days of the ram, but multiplied by fantastic speed. A missile traveling at Mach 5 to Mach 10 possesses so much energy that it can destroy a massive ship even without explosives, simply through the sheer force of its mass on impact. Naval weaponry has come a long way, from a wooden beam on the bow of a boat to smart bolides screaming at the edge of space, but the core principle remains the same. Find the enemy's weak spot and deliver the maximum amount of energy in the shortest possible time. Subscribe to the channel, hit the bell icon so you don't miss the next breakdown. Let me know in the comments which era of naval warfare fascinates you the most. Ancient rams or modern missile duels? I'm looking forward to reading your thoughts. Thanks for watching until the end. See you in the next video.